Hello, how are you guys? I hope you had a nice long break, and I hope that everybody is in good health and all your families are okay. So, a couple announcements. The homework 5, we are accepting it as end time until Monday today at 9 a.m. in the morning. If you haven't submitted it, submit it because you need to go over the stuff that's there. It would be useful to you, and we'll see about a penalty or something for late submissions. There is the abstract and the title of your projects. You should work on that and submit it on time. And the deadline is this Friday. You should have you should be checking your Canvas. You should be checking your announcements. You should be checking that regularly. I am in my portion, which might be today and maybe this recording and maybe another short recording. I will finish chapter 6, and then Professor Jay Mijra will pick up after that, starting from chapter 7. So in the last, before that, I will record all my portions offline, then we'll upload them, you watch them, and then send me questions in the discussion that I will open for that purpose. So last time we did we did a review of the gates and stuff that was covered in chapter 5. We started chapter 6. We finished chapter 6, section 6.1, and today we'll work on section 6.2. So we are still doing quantum versions of classical computations, and what we are about to partake in is section 6.2, which is reversible implementations of classical circuits. The goal here is to turn arbitrary classical Boolean circuits into reversible classical circuits of comparable computational efficiency. And by computational efficiency, most of the time we mean bounds on things. There has to be some limits on things. So the efficiency here is measured by two things: the number of bits we are using and the number of gates. When we talk about gates here, basically we are talking about Toffoli gates, which using Toffoli gates we can implement AND gates, and negation gates, which we can do an inverse, a NOT. So using an AND and a NOT, we can implement anything. So trivial substitutions of the quantum Toffoli and the X gates for the classical counterparts can do the trick of converting a reversible classical Boolean circuit into a quantum counterpart. Once we have an efficient implementation of a Toffoli gate, then we know how to obtain a quantum implementation of the same efficiency. Now, let us move to what is called a naive reversible implementation of classical circuits into quantum circuits. Now, a few definitions. Let us consider a classical machine consisting of a register of bits and a processing unit. that processing unit performs simple Boolean operations or gates on one or two or a few of the bits in the register. So let us take an example to be a classical 4-bit conjunction. The book uses the term conjunction, and a conjunction is simply just an AND gate. So in the book, in figure 6.2, it is trying to implement an AND operation of 4 bits, 4 Boolean bits, N3, N2, N1, N0. And note that the way these are ordered is N0 is the least significant bit and N3 is the most significant bit. But anyways, to do that, and assuming you only have 2 input bit AND gates, this symbol is the symbol for AND gates. You AND bit N3 and N2, you'd get N3 and N2 here, and then you cascade that in the AND with N1, you get the AND of bits N1, N2, N3. Then you AND it with N0, you get the AND of all the bits. And like what we said before, this hat symbol is the AND symbol in the convention of the book. So this implementation is clearly not reversible, right? There is the output, but all what you have, the final output of the AND of the 4 inputs, and you have ANDs of the previous 3 bits, 2 bits, and then a single bit, you cannot get N0, N1, and N2 out of this. So this is clearly irreversible. So if the machine, the machine that we talked about, that we assumed, reuses bits in the register, the machine loses information. And losing information, by definition, makes it an irreversible operation. So let us move on to figure 6.3, where we try to implement, similar to the above implementation, a reversible classical circuit for 4-bit AND. So if you remember, when we talked about the Toffoli gate, the Toffoli gate is basically a doubly controlled inverter. So if N3 and N2 both are true, then this is the basic Toffoli gate. Then the output will inverse what's on the third or the control input. In this case, T0 is 1. So N3, N2, if both of them are, if N3 is 1 and N2 is 1, so thus N3 and N2, we get 1, which is the inverse of 0, which is the input. So then we get here N3 and N2. And this is according to, if you still remember what we did last time before the break and this in the lecture, this was the implementation of an AND gate. So basically we'll do cascading. Then we take the input, the control output from the Toffoli gate, then add to it another input bit, N1, and then another kind of temporary bit, that's 0. That bit, when it comes out, will be the result of this Toffoli gate. Here, this N3 and N2 passes through, N1 passes through. Here, we would get the AND of this and this, which were here and here, so we would get the AND of N1, N2, and N3 in here. Then we further cascade. Note that here, these bits go through from this without any changes. This goes through, this goes through. The only bit that changes is this target bit. Now, in the third Toffoli gate, again, it's a cascade like what you see. The output of this is fed into the input of this, and the output of this is fed into the input of this. So here you have N3, N2, and 1 all ANDed. Then you add N0, and then you add another 0 bit, and we are calling it M0. We would get what is here, we get it back out, so we get N3, N2, N1 all ended. Then we get N0, and then we get at the end here, N3 ended with N2, ended with N1, ended with N0. So let us take a look at this. So clearly this is reversal. We have the output, right? We have the input bits, N0, N1, N2, N3. But we have some intermediate results that maybe are not really needed. We are here seeking a 4-bit AND gate, but we are getting the result for a 3-bit AND gate and a 2-bit AND gate of some other bits. So this is, once again, the Toffoli gate. So when you have A and B, they pass through. If you have a 0 on it, it's A and B and the inverse of the bit that's here. So this is 0 inverse, which is 1, then it becomes A and B. So in this implementation, we have the same number of gates as the above and the gate thing, but this is reversible, but also we have more extra outputs that we are not needing. We do not need these outputs, which are being outputted here as well. So this last example is a converted reversible 4-bit AND gate. We assign the result of each output to a new bit. And we remember that the NOT with the AND or the Toffoli gate form a complete set of Boolean operations. Basically, this is an AND gate. If you combine the two, it's an AND gate, and using an AND gate alone, you can implement anything. So an AND and a NOT, you can implement any combinational circuit, anything that's Boolean, any Boolean function. This implementation needs an additional bit for every AND gate or T Toffoli gate that's performed. And the additional gate is that 0 bit that was in the example from above here, right? So for this gate, for this Toffoli gate, you need this additional bit. For this Toffoli gate, you need this additional bit. For this Toffoli gate, you need this additional bit. Basically, because each gate is reversible, you have 3 inputs and 3 things come out. The result is basically the target, though you need to have a bit in the input that this is going to be modified. So we have T0, T1, and M0, 1 extra bit bare Toffoli gate. If the original computation takes T steps here, you can think of those as the 3 Toffoli sequence, the cascading of the gates. Then the reversible one, naively constructed, requires up to T additional bits of space. So you have T steps and T additional bits. The additional space is not in the 0 state, i.e. it cannot be reused. Basically, the extra outputs that are here, that are at the output here that I have in the yellow highlight, this is the output that you are looking for. These are the inputs, N0, N1, N2, N3, but we have N3 and N2, N3 and N2 and N1. These 2 bits, they are not in a reusable state. They are not in the 0 state, they are something. They are a function of some of these, of the bits. So they are not reusable again. So space here is kind of being wasted. So we cannot reuse these bits in quantum or in reversible computing. In quantum computing, we cannot just reset these bits to 0 so that we can reuse them again. And it goes without saying that such a transformation where you reset the bits to 0 is not reversible. And if you go to the back of the slides, you'd see that I constructed a simple truth table in some auxiliary slides where if you get a 0, you want to output a 0. If you get a 1, you output a 0. So when you see the output as a 0, what was the input? So that operation is irreversible. Thus, resetting is not an option in reversible computing for our purposes. But what we can do is, since the operations we are working with are reversible, is we can, though, do what's called, we can uncompute. And uncompute on any bit set. And uncompute means here is that we are using the fact that the operations, the computations are reversible. Reversible meaning we can go from input to output and we can go from output to input. Basically, the idea here is those results, the ones that I had in yellow here, can we uncompute them and recover that space? That's the idea we are after here. That's the idea of uncomputing. So in example 6.2.1, you'd see in figure 6.3 in the previous example where we did the 4-bit AND gate, bits T1 and T0, and by the way, there is a typo on those in the book, in the figure. I think the book calls them T2 and T1, but they should be T1 and T0. These are basically temporary bits or intermediate bits. They are used to obtain, to generate some of the intermediate results we use in the cascade to get the final result. That's eventually going to be in the bit denoted by M0. So if we look at an example where we uncompute to reclaim the space, this is in figure 6.4 in the book. Basically, we reverse all but the last step of the circuit. So I don't want you to get lost here. We want to compute something. We computed it, but we got other intermediate results that maybe they represent an entanglement of states, right? So we cannot reuse them unless we reset them. And we cannot reset them because resetting is reset them to 0 or even to a 1. That's unfeasible because that operation is irreversible. And then if it's irreversible, it's not unitary transformation, then quantum doesn't work on it, right? So what we can do is, once we compute, we get those intermediate results, we need to do uncompute on the intermediate results to reclaim those bits to use them for something else later. So basically, we are gonna be reversing all but the last step of the circuit in the previous figure 6.3. So the temporary bits will be reclaimed at the cost of, basically, we are gonna add more steps to it. So if we look at this figure, this T and this T and this T, the 3 Toffolies here generate the output. The output is this last bit. This one is generating T0. This was in the previous thing is one of the temporary bits. This one is N1, right? This one is another temporary bit. This is N2, this is N3. We take those 3 gates, right? Those 1, 2, 3, 1, 2, 3. We take this output. So this gate is producing the output. We are not touching it. This is generating N0. We are not touching it. This is N3, N2, N1 all ANDed. We take the output of this, which is really here, feed it into another Toffoli gate, right? And lo and behold, what is the inverse of a Toffoli gate? The inverse of a Toffoli gate is another Toffoli gate. Just you take the inputs, you apply Toffoli again, you get sorry, you take the outputs and make them the input to a Toffoli gate. The output will be the original input of the Toffoli gate. So we take N3 and N2, N1, N3, and N2 and N1 into another Toffoli gate. This would get us N3, N2 go pass, N1 go pass, and then because of Toffoli, we would get here a 0. Basically, this gate would do the inverse of this one. So it would get a 0. So we reclaimed that bit back again. We get N1, which was the input, and then we have here N3 and N2. We take the output here, which is N3 and N2, feed it into another Toffoli gate, we'd get N3, N2, and a 0. So that 0 is basically the uncomputed value of the intermediate value, which matches this. So these were the two auxiliary bits, or the two intermediate bits that we uncomputed here to recover. So in this implementation, we basically uncomputed these two bits, so they are internal to the big square over here that we have around us. The inputs are N3, N2, N1, N0, and a 0 bit, right, for the output. And then we see this is the output, and then N0, N1, N2, N3. So now we have a reversible implementation that doesn't use extra space and doesn't does not go in more steps. But that recovery of the bits came at the cost of those two extra gates. So basically, we kind of doubled the gates that we need, but we used less bits. So there is what's called here a trade-off between the number of gates and the number of bits needed. So you need to convince yourself that a Toffoli gate is really the inverse of itself, and I have done that also at the back of the slides in, I think, page 10 or 9 or something, and you can convince yourself there that this is the case, and it is. A Toffoli is the inverse of itself. So let us look at another example. It's example 6.2.2. In this example, we need to implement basically a, let me unzoom this a little bit so that you can see the entire page. Yeah. So we want to implement here an 8-bit conjunction, an AND gate of 8 bits. So again, it's a cascading of things, but we still need to do the reversibility and the recovery of the intermediate results. And to do that, since we have implemented a 4-bit conjunction in the previous example, we're going to use it as a box. So that and the 4 that hat with a 4 means this is kind of, you can consider it as a Toffoli gate of 4 control inputs, and this is what you are inverting. So if all these are true, N4, N5, N6, N7, if all these are true, you inverse that bit. So if this and this and this and this are true, N7, N6, N5, N4, we inverse this as 1, so this is the output. So for this, we use the gate we implemented in the previous slide, and then we get N7, N6, N5, N4, and then the AND of the 4 bits. We do the same with the other 4 bits, N0, N1, N2, N3, and then another 0 bit for the output, and then we'd get N3, N2, N1, N0, and then here we'd get what we are highlighting here, which is the AND of bits N3 to N0. Now, to generate the output, we have now two intermediate bits, this one and this one. So we AND them using a regular to Foley gate that had two is a regular two control inputs, one target bit, and then we have at the output the AND of all bits from N7 to N0. Now, this portion, which is this and 4-bit AND gate and this 4-bit AND gate and this 2-bit AND gate, until here, if we cut the circuit this way, we have implemented it. But we have, again, this yellow and this yellow. These are intermediate bits that we don't necessarily need. Can we recover them? The answer is yes, we can. So this bit and this bit are auxiliary bits, are temporary bits, are intermediate bits for the intermediate results. So we need to uncompute this and uncompute that. So we take these 4 inputs, right? And we feed, not that this goes down to this computation, but it comes out here as well as is. It's as if it went through like this. Also, this intermediate result goes here, comes out, and then we feed it in the bottom one. So this is basically getting the outputs here, which are the inputs here, and the output bit, which is here. When you do that, the inverse of this, right? You'd get the output and a 0. So now we've reclaimed the space. Or basically we de-entangled this, and you'll hear this towards the end of the section, the idea of that uncomputing kind of de-entangles that result from the rest. Same goes here, we are inversing this, getting bits from N0 to N3, and then we recovered that bit from that intermediate result to 0. So that's all what I wanted from this bit. Let us move on to the next slide. Let me make this fit. So now the circuit in figure 6.5, which is the previous page, which is the 8-bit AND gate, uses 2 temporary bits, the labeled, which the ones on the left, which were labeled with a 0, which I highlight them as the intermediate results in yellow. These are 2 intermediate bits. Besides, we have also 2 other temporary bits that are used inside for each of the 4-bit AND gates. This is at the cost of more gates. We recovered the bits, right? But we added more gates. So in reversible computing, the art or the magic, if you will, is that in these designs, we need to know or choose carefully when and what to uncompute. If there is an intermediate result, you know that you'll need at a later stage or at a later computation, you should keep it. You should not uncompute it, because if you uncompute it, you need to recompute it back later. So basically, this can be a positive trade-off that basically we are trading off additional gates for a more efficient use of space. This is a key statement in this section. Now let us move to section 6.2.2. So this section tries to arrive to a general construction for this conversion, and it also is trying to find bounds on the generated reversible gates where it shows that the the reversible implementation is almost as efficient as, or has little overhead on top of the regular classical implementation. So the goal here is to show that any classical circuit using T gates and S bits has a reversible counterpart that uses only order T gates to the power of 1 plus epsilon, that's in terms of gates, and order S log T bits. So the O notation is something the CS people should know, the ECE people should know, but there is some notation about it in the book, in one of the boxes. I believe it's called box 6.1, and I will try to put something on campus, a video or something that goes over that notation. But basically that notation tells you that this is an upper bound on the complexity of this particular thing. So in the case of the upper bound on the gates, it's order T to the 1 plus epsilon, and in terms of bits, it's O order of S log T. So if T, which is the number of gates, is much larger than the number of bits S, then this construction would use significantly less space than S plus T, which is the naive approach. The naive approach basically does S plus T. So if T is much larger than S, then these upper bounds are much less than S plus T, because then log the log for T and then times S and all, and T plus 1 plus epsilon, and if epsilon is small, then that's not significant. So I don't want to go over the details of the derivation there. It is there, it walks you through the steps, you can follow it if you want, but we don't necessarily need that much details. Basically, it shows that for a circuit with T steps and S bits, it can be done reversibly in order T to the log base 2 of 3 steps and order S log 2 T base 2 bits. The book goes into the details of the derivation, and it shows that for any epsilon that's larger than 0, the number of gates required for the reversible computation is really T to the 1 plus epsilon, and the space bound is still S log base 2T. So for the notion of bounds, upper and lower, you can bound anything from the lower level and the upper level. You have a ceiling and a floor. You can find that in page 107 in box 6.1. It goes over the notion of the upper and lower bounds. Basically, there is 3 figures in this section that show conversions of a classical circuit to a reversible one, a reversible but inefficient implementation, and then a reversible implementation that reclaims storage. So using quantum circuits consisting of entirely Toffoli and X gates, reversible versions of classical Boolean circuits can be implemented. So not only this, but actually any classical Turing machine, and again, this is a term the CS students should understand well as the computer engineering students should also understand that. But basically a Turing machine is something in finite automata where it's a machine of certain things that it does and things like these. So again, just if you want, go Google Turing machines, and there should be videos that describe this. I can point you to some things that goes there. But basically, again, it's another generalization. It's not just any Boolean thing, but any Turing machine. So this is a more generic computational model. So this is saying that we can convert any classical Turing machine into a reversible one. So for qubits, the importance of, or the need for uncomputing values is even greater. If you remember when Philip was talking about quantum supremacy, it was in the order of quantum supremacy, we think is in the order of 49 bits, 50 bits, or 53 bits, or something like this. So the number of bits is not that big. But since the number of bits is limited, and if you are using and get like an 8-bit thing, and then you use all these extra temporary bits and you don't reclaim them, then in a very short period of time, without doing much computation, you've ran out of bits already. So uncomputing values is even of greater importance in quantum computing. So uncomputing ensures that the temporary bits also, the temporary qubits, are no longer entangled with the output qubits. So that entanglement means you cannot use these bits for anything else. You need to de-entangle them or unentangle them. Not sure is it de-entangle or unentangle, but unentangle is what's in the book. So unentangling the temporary values is one major difference between classical and quantum implementations. In a regular classical circuit, you computed a value that you don't need, you just throw away, you don't care about because it doesn't affect the rest of your results. But in quantum, these bits would be entangled with other things, and you don't want to do that. You need to unentangle them, de-entangle them, so that you can reclaim the space and do the computation. So uncomputing temporary qubits disentangles them from the rest of the system. So these are my temporary nodes, or my support nodes, I'm calling them. This is, recall that this is the Toffoli gate. This is going through the case where this is the generic Toffoli gate with ABC inputs. This would be the output. This is the case when the input is 0. This is the case where if you have an input that can be a 0 or a 1 and you want the output to be 0, basically that's a circuit where the output is connected to the ground and then the input is just floating. You're not doing anything to it. So this is clearly irreversible. Then the last one is I wanted to show that if you have N3, N2, and you have N3 and N2 ANDed together, and you apply them, and you apply the Toffoli gate up here, A, B, C input, C inverse. So N3 and N2, this is the inputs here, and C, which is the third input, the target input inverse. So basically this is ANDed with itself but inverted. So a value is ANDed with its inverse. If the value, if N3 and N2 is 1, ANDed with a 0, you'd get a 0. If N3 and N2 is 0 and you end it with a 1, the outcome is a 0 step. So basically, in either case, when you do this, you'd get N3, N2, and a 0, which looks like you've inverted really the Toffoli gate. The inputs became the outputs, which shows, this proves that the Toffoli gate is the inverse of itself. This is another thing that I went ahead and was trying to show that the four input Toffoli gate, it's the inverse of itself. Basically, this is multiply controlled N7, N6, N5, N4 controlled negation gate. So if you get the AND of all these bits, and then these bits individually, you would get the individual bits and a 0. And again, this is C, like C in the previous page, inverse, ANDed with the AND of bits N4 to N7 or N7 to N4. And then again, this would give you a 0. So that's it for this portion of chapter 6. I have another portion that will be in another video. So I still have some. I want to go a little bit about section 6.3 and some of the stuff in section 6.4 to prepare you for the stuff that Jay is gonna do with you. So I'm sorry for the delay in the recording and in uploading, but I didn't want you to be, since we are trapped at home, I didn't want you to see the kids running around and all the voices and the stuff. So thank you very much. And if you have questions, please post them to the discussion board that I will create. I'll call it lecture discussions or something like that. I use the announcements on Canvas a lot, so make sure that you check there frequently, and if you're not getting the emails, you should be getting the emails. Okay, thank you guys, and that's all for today. Have a great week, and I hope that business of online stuff goes well. Ideally, I would have done this in Thomas and Brown 304, which has a big whiteboard, and I would write on the board and all that stuff. Or I could have created PowerPoints, but that would have taken quite some time, and we didn't have that much luxury, unfortunately. But thank you very much, and please, if you have any questions, let me know. Bye-bye.